Good morning. Welcome to Krishna's classroom. Now we explore further how the fundamental theorem of calculus manifests in the context of Lebesgue integrable functions. We call the classical relationship between the derivative of a function and the function through what is called the antiderivative. That is, if f derivative, if f is a given function which is differentiable, I am not very precise here, assuming sufficient smoothness or everything is there on some interval ab, then f derivative equal to a given function f. Suppose f is a given function and we want to find out small f such that f derivative is equal to, then in the early days it was believed that for any given f, such a small f exists. But this notion had to be revised in the context of further knowledge about integral, especially when the Riemann integration theory or theory of Riemann integral came into being. So they had to revise the whole notion at that stage, and then it was found that the relation between the function and its antiderivative is not something as simple as one imagines about it. Well, there may be functions for which the antiderivative, the relationship between, see, if this is the case, then we found that this is essentially f is, or small f is integral, indefinite integral f t dt. This was the indefinite integral that we wrote, and then we said that the relation is f derivative, or in other words, f is essentially, this is the sort of relationship that emerges. That is what we were initially told that, and this actually contains the fundamental theorem of calculus. So wherever such a thing holds, then it is found that fb minus fa assuming all the conditions required for such a smoothness required for such a relation. Now when we ask more deeper questions, like for which class of functions such a relation would hold, then the problem becomes not as straightforward as it appears to be, and that's the problem that we encountered when the concept of integration was reformulated in terms of as the Riemann. Then of course we were seeing that there are a lot of inadequacies that come around, and then the theory of Lebesgue integration came, the concept of Lebesgue measure came, and consequently the Lebesgue integration theory. And then of course we start asking the similar questions that you have. For what class of functions a relation of this kind is valid, where you are talking about the integral that you are talking about is the Lebesgue. So let us So that is the problem. Now we have already characterized absolutely continuous functions. And we found that our investigations have shown that if the function is very rapidly oscillating, put in inverted commas, then you have to expect trouble, because what happens is the derivatives become very large, very frequent. That is one problem. And again, when you keep the function folded, something like this, say, a continuous function, something like x sine 1 by x or something like that, it gets folded. Now you see that even over a small interval, if you split it into smaller intervals and I mean smaller disjoint intervals, then the total length or mod fxi, something like this, sigma, becomes very large. That is because of the rapid acceleration that is taking place, such functions. And we have already seen some examples in this context. So we need some kind of a restriction on this type of sum, and this has been brought into the context through defining or by defining what are called absolutely continuous functions. So we have done some research on absolutely continuous functions, and we have given a characterization already of absolutely continuous functions, and we make use of that to explore these functions further. Okay. So let be a continuous function on the interval. Now we look at the discrete formulation of the fundamental theorem of integral calculus. What does it say? This is the fundamental theorem of discrete calculus, and we are going to write down the discrete formulation of this, and the discrete formulation of this of the fundamental theorem of calculus, which is given above in the box, takes the form integral over a to b average difference which we have defined earlier. This is equal to average value of f at b minus average value of over h now that is what you have is the following: integral a to b h. To be precise, you have to extend this on the interval t belonging to A B plus 1. Now here we are restricting x to this is equal to integral b to b plus h. Having extended the function to from AB to A to B plus 1, you see that all this is well defined. I mean, we have already said that you extend the function from over B to B plus 1 by defining the function to be equal to FB. It's a constant, so that you still maintain the continuity. Now, this is what you did. Now, since f is continuous, limit now we show that okay, this is what you did. Therefore, that's how this comes. Therefore, you have to look at this one. So, what happens to the limit of as 0? Now, the problem that you have is this. As h tends to 0, you want to take the limit of this integral. It will be nice if you can jump the integral. The limiting process can jump the integral and go inside. So if that happens, then you see that this becomes what is called the limit as h tends to 0. This becomes the f derivative. Okay, and you end up with this. So the question is that when we can assert that when we can assert that That means when you can actually jump over the integral, or in other words, the two operations of the limiting operation and the integral operation would commute. So this is the question next. That is the commutativity of or what? The and this is the question. If they commute, you can go inside and write this. This will be justified and so on. So what are the conditions that you need on F so that this is satisfied? Now, in this context, we gave the intuitive notion that the control has to be exercised on the oscillation of the function, because if the function oscillates too rapidly, then you see that the derivatives are going to be unbounded, or this difference f over h, which is this one, as h tends to 0 would become very large. So such things have to be controlled. So we have the following theorem. And if this is valid, then of course you see that this tends to f derivative. Okay. So you will end up with this tend towards f derivative if such a limiting process works. Okay. So the theorem, the statement of the theorem is that let then f is differentiable almost everywhere comma its derivative f derivative is integrable and you have the following results, which is the fundamental theorem of calculus, integral calculus. Integral a to b f derivative so a sufficient condition for this to be true is that f is absolutely continuous on Okay, let's first prove this. And then later we can see that this is also a necessary condition. And therefore, you get a beautiful theorem. It says that if f is absolutely continuous over AB, then the fundamental theorem of calculus holds. Yep. So we first prove this. Okay. The discrete formulation of the fundamental theorem of integral calculus is for all in fact it is valid for all continuous functions now choose one by n. So h tending to infinity. Now and letting n tend to infinity is equivalent to 1 by n 0 plus we have equal to, now this part goes over to because this one we are using this. So let us now use this. Okay. Now look at this collection of functions. Now f belonging to absolutely continuous over AB implies f is equal to G minus H, where G and H are non-negative increasing functions increasing absolutely continuous functions on the interval AB. So these three properties are non-negative, increasing, and absolutely continuous. Therefore, find these functions are differentiable almost everywhere, and what we get is this. On the open interval AB. Now, since in fact this does not require absolute continuous. Now what you have is, since f belongs to absolutely continuous AB, by the previous theorem implies difference function, the average difference function is uniformly integrable Now, this is what we have proved in the last lecture. That is, if f is absolutely continuous, then the collection of difference functions, say difference function, difference 1 by n, f is uniformly integrable on AB. Now, since we are taking h equal to 1 by n, this collection is a countable function. So, this is uniformly integrable. Now, for such functions, the Vitalis convergence theorem, hence by Vitalis convergence theorem, one can interchange the integration and the limitations. and integration. And consequently, which is equal to integral a to f derivative t f derivative. Okay. Therefore, integral a to b as we have mentioned earlier, the other side of average functions, you have them going to the limits fb minus. Therefore, what we have proved is that, so this completes the proof here. So what we have proved is that the function is absolutely continuous, then for such functions, the fundamental theorem of calculus or integral calculus holds good. Okay. Absolute continuity is a sufficient condition for the validity of fundamental theorem of integral calculus. Okay, so if so, you would like to ask further, could this be also a necessary condition? So the question that immediately comes up is this. Let us explore this. So that's the basic question that we are looking. So if we can establish that it's also a necessary condition, then it follows that absolute continuity of f is equivalent to saying that the function satisfies the fundamental theorem of fundamental theorem of calculus, integral calculus. So before that, we make a definition. We call the indefinite. F closed bounded interval AB the indefinite integral of G belonging to G defined on provided G is Lebesgue integral. Over AB and f of x G for every x belonging to it. So this is a representation. That is, f can be represented as the integral of the indefinite integral of a function g. Okay? So that f derivative would become g. So we shall now state the central result, namely that f is an absolutely continuous function on the interval AB, then it admits the representation as an indefinite. Conversely, if a function admits the form of an indefinite integral as we have defined above, then the function is absolutely continuous. Okay. So we state the theorem. This is an important result because it settles in either way with no gaps left that the only functions for which the fundamental theorem of integral calculus holds in the context of Lebesgue integration are the absolutely continuous functions and vice versa. A function f on a closed Most bounded interval AB is absolutely continuous if and only if it is an indefinite integral over the proof. We first prove, see, this is a necessary and sufficient if and only. First prove or restate the proof of the forward implication. That is, if f is absolutely continuous, then it is an indefinite integral over. Conversely, if the function is an indefinite integral over, then it is absolutely continuous. So we prove the first part. So we assume is absolutely continuous over the curve. Then for every x belonging to f belongs to that means for every subinterval of the form a to x, the function is absolutely. So that's a very simple elementary truth, which then implies by the previous theorem and that means what we have proved, f derivative exists almost everywhere and is integrable over a to x. Further, f of x equal to f of a plus integral a to x f derivative. That is applied to the interval a to x, you get this result. This is true for every x thus what we infer is that f is the indefinite integral of f derivative. F derivative. on the interval. So we have proved the forward implication. Now let us prove the backward implication. What we assume is this. F is an indefinite integral over of a function g, that is now we claim, or what we claim is this. Claim f is absolutely continuous on the interval. Let us prove the. It's very easy to prove. Not much work left. Let be a collection of open intervals, disjoint open intervals in A. Now define E to be the union of these disjoint intervals. That's the definition. Then, by the monotonicity and additivity, over domains, properties of the integral we have sigma This is K running from, and this is of course less than or equal to and that is of course equal to integral over E of, so we shall use this relation to prove the absolute continuity of. So let epsilon positive be. Now since G is integrable over AB, there exists a delta positive such that integral over E measurable because the measurability, this becomes a measurable function, therefore the integral would make sense. And measure of E is less than delta. Now that gives, which implies for the choice of delta, sigma is less than epsilon, and our E has measure less than delta. Whenever measure of E that is when f belongs to, f is absolutely continuous over whatever. So we have proved a very powerful result. It says that the only functions for which the fundamental theorem of integral calculus holds is the class of absolutely continuous functions and vice versa. So that was the one that we were all the time trying to establish or trying to search out for which class of functions this would hold. So this theorem completes our task in this regard. Now we will look at some of the consequences in the next lecture. Thank you very much.